you split the universe up into spheres. So take your origin where we are, take a sphere of radius r, take a shell of thickness delta r, and the point about it is that the volume of this shell is proportional to r squared delta r. So the number of sources there, if they're uniformly distributed, is proportional to r squared delta r. Now, the light from each source, each star there, comes to us, and the light decays with the inverse square law. And so the flux per shell, the amount of radiation you receive at the center from the shell, is that times that, and the r squared cancels with the 1 over r squared. That is the crucial feature. We have just seen the importance of the inverse square law. The r squared and the 1 over r squared cancel. So the flux of radiation received here, the amount of light, is proportional to delta r, and is therefore independent of how far that shell is away from us. This was the immensely important discovery of Orbis and Halley. So what that means is if you integrate all the shells from 0 to infinity, you get a divergent result. The amount of radiation in a simple model at the Earth should be divergent, because all of those shells, you've got to keep going to infinity, because each shell, no matter how far or how close, gives you the same contribution to the light received at the Earth. Well, that's a disaster, and what it tells you is you cannot ignore the most distant sources in the universe when you calculate what's happening here, because no matter how far away they are, no matter how faint they are, their numbers add up so that the total radiation is totally not negligible. Now, that's a flat space calculation, and it ignores the fact that the nearest stars actually block off the light from the further ones. If you take that into account, it shouldn't diverge, but rather what should happen is that the surface density here should be the same, of the intensity of radiation should be the same as the surface of the sun. Okay. In curved space-times, we replace this calculation by a more complicated one. This result here is true in any curved space-time. The received intensity of radiation in any direction is given by the spectrum of the redshifted spectrum of the radiation at the source times the surface brightness of the source divided by 1 plus z cubed. This follows from the equations I gave you yesterday, and it is in those notes. The derivation of this result is in the notes that I gave you. And this is a realistic calculation of the background radiation in the universe, which we can use in the context of general relativity. That's a correct equation. Now, there are new factors which come in here, and the most important is that the distant sources appear fainter than nearby because the universe is expanding. So the radiation, because of the expansion of the universe, the radiation from those distant sources is not the same after all. It decreases as 1 plus z cubed, and that then is sufficient to solve the Orbis paradox for you. Now, there's another feature also, that the universe has a finite age. And so, in fact, in the universe, the initial model people had in the old days, before they had serious cosmological models, you just had stars going forever. But, of course, that isn't true. In fact, you chop off this integral at the time of the surface of last scattering. So that's the next important effect that happens here. Yeah?
So would you go as far as to say Orbis paradox implies that the universe must be expanding? We don't even need any other evidence?
I think that's actually a pretty good deduction, yeah. That if you thought about it long enough, Einstein, with his Einstein static universe, he didn't think about thermodynamics in the Einstein static universe, and he would have realized that transient thermodynamics doesn't make sense in a universe which lasts an infinite time. Actually, you can argue against the Einstein static universe from thermodynamic basis, yeah.
But you need the expansion. The finite age alone is not enough, right? Because finite age still would integrate out to a very big value.
Yeah, yeah. So the second point is that the most distant light we receive is from the surface of last scattering at a redshift of 1100, a temperature of 4000. So in fact, the integral doesn't go on forever. It stops at the surface of last scattering. So most lines of sight don't end on stars, which would be the case if the universe carried on forever. Instead, they end on this last scattering surface, and the radiation which we receive from that surface is the cosmic background radiation at its temperature of 4,000 divided by 1,100, approximately 2.75. So in fact, the current statement from Orbis, the integrated light, actually the stars, because of the cutoff plus the redshift, the stars do not give us as much radiation. In fact, they give us also about 3 degrees K, a factor which was known quite a long while ago. But the dominant radiation is the cosmic background radiation, and that's the sort of current Orbis interpretation. The integrated radiation from all discrete sources is much less in comparison. And one point about this is most galaxies are transparent. It's something that is very misleading when you look at a picture of a galaxy and you get the impression that the galaxy is kind of solid, that if you fired a bullet through a galaxy, it would hit a star. In fact, that's not the case. What is happening is in those pictures of galaxies, the optics are spreading out the light from each star and making it look like as if it's solid, but in fact the chances of hitting a star if you fire a bullet through a galaxy is about 10 to the minus 5. They basically are actually totally transparent. So, the present-day Orbis calculation has 2 parts. The integrated emission from all discrete sources at all wavelengths, plus from the intergalactic medium, and in fact there's a whole branch of astrophysics which looks at the integration of distant sources and how that leads to background radiation in addition to the 3 degree K blackbody radiation. Nowadays, when people say background radiation, you say 3 degree K blackbody, but actually there is background radiation at all wavelengths from X-ray sources, radio sources, and so on, and there's a whole branch of astrophysics looking at this integrated emission from all distant sources. Then there's the detailed analysis of the radiation from the last scattering surface, the angular power spectrum and its detailed analysis, which I very briefly mentioned yesterday, and which will be discussed later by Professor Dunsby in this course. And so that spectrum of radiation, that's where Orbis is in practical terms in the universe today. Now, there's an anthropic version of Orbis. And this is something which has been sort of realized fairly recently. It's obvious once you realize it. The Earth is in contact with the thermal reservoir at 2.75 K, and that is crucial for the thermodynamic functioning of the Earth. It's this reservoir, the dark night sky, acting as a thermal reservoir, which is the heat sink into which we dispose of all the entropy generated by our activity and by the biosphere. So what actually happens? Looking at the Earth as a thermal system, the sun is the heat source at 6,000 degree K. We receive the radiation from the sun. We utilize it in the biosphere. We radiate off, and this is the sink. So as a heat engine, that's the heat source, and that's the heat sink. And if the heat sink was not there at that lower temperature than the source, life would not be possible on Earth. It is the sky temperature. If the sky temperature were 300 K or above, life would be impossible. So from this viewpoint, the reason the sky is dark at night is because if this was not so, we wouldn't be here to see it. Okay. That's the anthropic version of this story. Now, there's a gravitational version of Orbis paradox. The same issue arises for Newtonian gravity because it's also an inverse square law. We just saw this beautiful derivation of where the inverse square law comes from. That means for gravity as well, most distant matter dominates. If you want to calculate the gravitational force here, you've got to keep integrating to infinity because exactly the same as we saw for the light, all those distant spheres count. And the present-day form of the problem is as follows. We're moving at 300 kilometers a second relative to the cosmic background radiation. I mentioned this to you, the dipole that we've measured. Why are we moving relative? Because there's a cosmic inhomogeneity pulling us, which has been called the great attractor. And there's a whole further branch of astrophysics which tries to work out the properties of the great attractor. There's an overdensity on one side and underdensity on one side. And the great attractor, in fact, Professor Farrell has spent a lot of time looking at this, is an overdensity of matter which is pulling us that way as opposed to that way. And that's where this 300 kilometers a second comes from. Now, so what you do is you take shells again as before. And on each shell, if it's overdense in one side, there's an excess force, which causes an acceleration and causes velocity. But the problem is, how do you know when you've taken the integral far enough? And this is a major problem for anybody who is calculating these velocities in the universe. Do you need to consider further distances? Now, the difference to Orbis, in Orbis, for the light, the integral was on the light cone, and so it cut off. Now, the difference here is there isn't any cutoff. There is no cutoff, and you've got to keep going on to infinity. Now, that's a real problem. It corresponds, the Newtonian theory corresponds to the relativistic constraint equations. You, in fact, feel the force instantaneously because it is a gravitational force which is conveyed by the constraint equations, not the time evolution equations. Actually, the gravitational, the Coulomb force doesn't come to us at the speed of light. It comes to us instantaneously. And that was actually hidden in the talk a little bit earlier. Actually, in that calculation, actually the forces also can come instantaneously, not at the speed of light. The constraint equations, the key point is when you set up the universe initially, you must satisfy the constraint equations, which satisfies the Gauss law for gravity and sets up the inverse square law in the initial surfaces. And then it is a major theorem of relativity theory that the constraint equations are preserved by the evolution equations if initially true. So once you've got the Gauss law satisfied initially, however things move, it will be satisfied later because the constraint equations are preserved by the evolution equations. So the initial conditions must satisfy the constraint equations, and then they'll be true at all time. Now, there's no natural cutoff of the integral in this case of calculating velocities locally, because you're doing it on these space-like surfaces. You're not doing it on time-like surfaces. You must, in principle, continue to spatial infinity. Each distance shell is just as important in causing motion here and now as the nearby ones. And this is the reason Newtonian cosmology was not arrived until long after relativistic cosmology was on the stocks. Newtonian cosmology, there are these divergences which people like Newton found they couldn't handle. However, what does save you to a considerable degree is the fact that Newtonian gravity is of vector nature. It's pulling you in one direction as opposed to the other. Hence, the shell effects cancel except if they're very anisotropic. If your shell is isotropic, each shell is pulling you in all directions, and the total effect, the residual effect, is zero if the shell is isotropic. So that's actually what helps you to get around this. In effect, because of that, you renormalize by omitting the divergent integral due to a uniform background. You only have to calculate the remnant effect due to the inhomogeneities on each shell as you go out. So what we, in effect, are doing when we do these calculations, we're assuming the matter further out is isotropically distributed at the larger scales, and then it has no local effect in terms of causing velocities. So then you can ask, could large-scale velocities then provide evidence of inhomogeneities outside the visual horizon? And the answer is yes, but in an integrated sense. Because you can work out that whatever is outside is causing you a certain velocity inside, but you can't separate it out into what is happening in different shells further out there. So it really is important here that this never converges. You have to always need to consider more and more matter. What you find in practice in people who calculate this is they go out as far as the latest catalog. And when they get a new catalog, when you go from galaxies to IRAS, then people calculate it out a bit more. And in each of these calculations of the great attractor, they stop the calculation when they've got as far as the latest catalog goes. Now, if you go to gravity itself, general relativity, then it's the tidal force you have to look at, which has a tensor nature. It's quadrupole. Now, that dies off fast. It goes as 1 over r cubed. So the tidal forces are quite different. It's given by the electric part of the Weyl tensor, for those who know the relativity. And so for the tidal forces, it's only the closest shell that matters because these decay at 1 over r cubed. The effect converges